So there's a homework. I hope you have some fun with it. It should be fun. And oh, also, as you know, there's no final class. And as I want to be a rule follower, we will have a final exam period where because I'm supposed to do that. I realize I've already heard from some of you that you might have travel plans. We will not send the factorization police after you if you're not here. If you're here, please come and endure my self-indulgent last class. But I mean, I understand if you've already been traveling. So, okay, questions?
What day is that gonna be?
I forget. It's going to be on Thursday. I'm pretty sure. Whatever the time period for this is, maybe it's 11:30 or something like that. It's 11:30 to 2 period on Thursday. Okay. So we were talking about the boundary map last time, and the last result that we had is this nifty result here that R is an HFD and a quotient field if omega and K is almost integral over R, then so loosely speaking, the number of factors in the numerator must be at least as much as the number of factors that you find in the denominator. This is going to come back maybe more than once. Okay, so what I want to do now is I want to talk about some more results about the boundary, give you some positive things, and then we're going to talk about HFDs. So let me kind of point out sort of a big picture thing here. Okay, so for factorization types, we know. So let me kind of give you sort of motivation. We have UFDs. And any UFD is an HFD. I'm going to tell you what a couple of these things are. Okay, we know what UFDs are. We know what HFDs are. We don't know what bounded is. We know what ACCP is. It means the ascending chain condition on principal ideals, and we know what atomic domains are. Right. And one of the things we proved early on is this implies this. Right. BFD is bounded factorization domain. Now, what does that mean? That means that given non-zero non-unit, X and R, there exists Bx, an upper bound on the links factorizations, irreducible factorization. So what it means to be a bounded factorization domain is there may be zillions and zillions of ways to factor this X, but given an X, there's an upper bound on how long that factorization can be. And this bound, of course, depends individually on X. What is an FFD? This is a finite factorization domain. See if you can guess what that means. Given non-zero non-unit, X and R, there are only finitely many irreducible factorizations. That's, by the way, let me say for both of this, that these are defined to be atomic. So it's atomic plus this condition, because you could certainly take, you could take a domain and only consider the ones that factor into irreducibles. So bounded factorization means atomic plus this hypothesis, and finite factorization domain means atomic plus this hypothesis as well. Another way to think of a finite factorization domain, atomic plus any non-zero non-unit has only finitely many different irreducible divisors up to associates. Okay, so once I tell you what this is, the fact that these implication arrows work are fairly straightforward. A UFD, well, UFD has both links of preserved and uniqueness, so certainly this is an implication. Half factorial domain has to be a bounded factorization domain, because taking any element, given any element, all of its factorizations have the same length, so there's your upper bound, right? If you have a UFD, it's certainly a finite factorization domain. In fact, UFDs are finite factorization domains that every element has only one factorization, right? And any finite factorization domain is clearly a bounded factorization domain because there's only finite many factorizations. This was a little bit of work, and this one's a little bit of work. The bounded implies ACC. It's not too bad. The interesting part is none of these implications are Parsons at all, right? None of these have factor error. For example, one of my favorite examples is this. This one is an HFD because any construction in this form is, talked about that earlier. And this factorization shows there are uncountably many factorizations of X squared because R has infinite transcendence degree over the reals. Right? This is a half factorial domain. So it's a bounded factorization domain, but it's not a finite factorization domain. Because a finite factorization domain, there's obviously too many factorizations here. Right? There are certainly finite factorization domains that aren't half factorial domains. For example, take any ring of integers class number bigger than 2. That's a finite factorization domain, but it's not an HFD. But the reason I bring this up is given, so this is motivation, given a factorization type, or in fact any domain, the domain can be, doesn't have to be factorization. Given any domain with a nice property, a very natural commutative algebra question to ask is, if R has property in some nice property that it has, does or X or localized at S, interval closure, complete interval closure. The power series, you can go on and on. I like to call these kind of things stability, values, right? If you have some nice property or ring, under what circumstances is it shared with polynomial ring, power series ring, localization, interval closure, complete interval closure? There's all kinds of natural constructions. Right? Thank you. Well, let's think about this, right? Of all of these properties, let's figure UFD is the king, not just because it's at the top of the food chain, but this is the only one that has a known universal ideal theoretic characterization. Far as the UFD, what about its polynomial ring? Yes. Closure completed. Go over all of these, but. For UFD, these are all guesses with one exception. You know, exception. We did this one actually in homework or in class and homework. This one's a well-known example. This one's interesting because the failure is not as bad as Palpatine like it, because if R is a PID, this is a yes. Localization of a UFD is a UFD. And these last two are yes because of cheating. Why?
Because it's intervally closed.
Any UFD is both interval, in fact, any UFD is completely close. So this is kind of cheat. HFD, which is sitting right next to UFD. In general. So we're going to explore this one a little bit. We're going to this one sort of follows from this one. We're not going to talk about this one too much. We're going to give an example here as well. This one's hard. This one's hard, but this falls from this as well. By the way, let me point out polynomials for all these factorization type domains, they always work, with this exception and one more. Anybody want to guess? So of these last four blocks, there's three yeses and a no. Anybody want to guess where the no is?
The atomic or so I feel like I remember that from your talk.
All the other ones, the other ones of these properties, I should say, that fail passage into the polynomial are half factorial domains and atomic domains. And I will say something about the atomic. The atomic is especially mystifying right? Because atomic would be sort of just thinking about it casually over a cup of coffee would be at the last of my list to fail. Right? Because think about it. Suppose that you have a ring that's atomic, that means that everything can be factored into atoms in the ring. Now you look at its polynomial. Well, do what comes naturally. Just take that polynomial and factor it down until it's at degrees that you can't break down anymore, right? You're eventually going to get stuck there because you're going to get stuck in the quotient field at some point. The degree will eventually, you can't go to degree -1, right? So eventually you get stuck there. All that leaves is the constant terms to factor out. And R is atomic. Nonetheless, it fails, right? Which is really weird. And here's sort of, this is very kind of intuitive, but it might be the case that AX plus B doesn't factor into atoms because you can always keep pulling something out of AX plus B, right? Which is really weird because A factors into atoms and B factors into atoms, but that doesn't mean that you can't rewrite this and keep pulling stuff out. And what's especially mystifying is the fact that every homomorphic image of this that doesn't take this to 0 of the unit must factor into irreducibles, right? So in other words, if you plug in 2 for X and it's not a 0 or a unit, it must factor. But nonetheless, when you kind of, when that variable holds this apart like that, you can see kind of pull things out. This is really weird. And I challenge you to look. This was in a paper by Reutemann in the early to mid 90s. Gave an example of an atomic domain whose polynomial ring is not atomic. Full disclosure, everybody that I know that claims to have read that paper says they don't understand it. So anyway, however, Reutemann is quite good at his examples, so I have pretty good faith in that. And was refereed. So anyway, it's actually among these properties, atomic is actually, in my opinion, sort of the most unstable and the one where there's the biggest kind of question marks. There's been a lot of work on how to reconcile this in sort of atomic domains. What else do you need to strengthen it up? What we are going to do now, so hopefully I've kind of motivated this a little bit. I'm going to look at the HFD case in particular and look at some of these properties. And of course, we see those across the board. However, there are some yeses in specific cases to this. Right? In fact, one of the things that I was preaching early on in the class is, oh, UFDs are so grand because they have an ideal theoretic characterization, right? Every non-zero prime ideal contains a non-zero prime element. HFDs actually behave. So, for example, in general, you get no's across the board. However, in a ring of algebraic integers, for a ring of algebraic integers, you get yeses across the board, as a matter of fact. And actually, it's interesting that I bring up that case because for rings of algebraic integers, there's an ideal theoretic characterization of HFDs. And that characterization is HFD if and only if the order of the class group is less than or equal to 2. So let's dive into some of this. We're going to go, we're going to use some of these results for boundary to show an interesting theorem about why HFDs are preserved in interval closures in certain cases. So the first thing I'm going to do is I'm going to start off with this little one here. Let's let R be an HFD. And not just any ring, I want this to have a special property such that no non-unit of T has boundary 0. That is to say, if X is non-zero, non-unit of T, then of course, as T is an ring, any X in T is a quotient of two things in R, right? And so you can measure its boundary because it's in the function field. Boundary is greater than 0. Notice a good candidate for this type of ring would be integral closure of R or complete integral closure of R, right? This doesn't quite get it because here's what I do know about the integral closure and the complete integral closure is the boundary of it. If T is the integral closure, the complete integral closure, the boundary of everything in T is greater than or equal to 0. And so this is just that on a little bit, with a little bit more juice. I don't want a non-zero non-unit to have boundary 0. Okay, so the following conditions. Number 1. The boundary of alpha is greater than or equal to 0 for all alpha and the non-zero elements of T. T is a unit. Well, I should say that T is a T. That's just really from the definition. No non-unit of R. The non-unit R and R becomes a unit T, and 4, every irreducible in R is also irreducible. So if you have something with these conditions, this enjoys all these conditions. Let me kind of go through some of this. First, a remark. No non-unit R and R becomes a unit in T. Anybody know another kind of extension that satisfies that? Integral extensions satisfy that, right? You can't go from a non-unit to a unit in an integral extension. So property 3 shows that this is kind of imitating that important part of integral extensions. And 4 is kind of neat too, because we saw this show up in our proof that z adjoint the square root of -3 was an HFD because the irreducibles downstairs remain irreducible upstairs. Proof. Suppose Um, Okay, so how do we counterbalance this? Well, suppose I have something negative bound. Right. So what I'm gonna do is I'm gonna get a non-zero, non-unit of boundary zero to contradict this. Uh, uh, so let me point out that I'm okay in making this mistake, because R is an HFD, so it has to have an irreducible. Because if it doesn't, then it's a field. And if R is a field, then T and R are the same thing, and the conclusion is true. Right? So let's let this be irreducible, and notice that the boundary of pi is equal to 1. And consider the element pi to the T alpha, right, which is a non-zero, non-unit. And notice that this is equal to T boundary R pi plus alpha of boundary alpha, which is T plus negative T, which is 0. And there's your contradiction. We have like a non-zero, non-unit of boundary 0. Number 2, if the boundary is 0, then it must be a unit because no non-unit T has boundary 0, so there you go. Fine. How about the other direction? So there exists therefore boundary 1 equals 0, which is boundary R ST, which is boundary RS, boundary RT. And from the previous part, we know that neither of these could be negative, right? And so if you sum two integers, neither of which could be negative, you get 0. This implies boundary RT must be 0. Right? Suppose R is an R, and R is also a unit by 2. Boundary R is 0, right? Because it's a unit. But R is in R, therefore boundary R. Remember, when you restrict the boundary down to the original rate, you get the wave function. That means R has zero or irreducible factors, therefore R is in star. So anything that becomes a unit of stairs had to have been in the first place. Finally, we want to show that irreducibles, there might be new irreducibles in T, but everything that's irreducible in R, when you look it up in T, it's irreducible. So 4, but pi and R is irreducible. And suppose pi is alpha beta with alpha beta and T. Once again, we see the power of the boundary map. This means that boundary pi is 1, and this is equal to boundary alpha plus boundary beta. Now these are non-negative, and they have to add up to 1. So without loss of generality, the boundary of one of them is 0, which implies alpha is a unit in T. Therefore, pi is irreducible in T. Any questions? Okay, so let's kind of get a little bit more in depth on this, and we'll see where this takes us. There, 13.2. Theorem 13.1.2. Suppose you are in a HFD with an overring T. So similar situation, HFD and T and overring such that no non-unit of T has boundary 0. Okay, so what we can gather, so this is the same setup as last time. Notice that we're really close here, right? You have that every irreducible pi in R is also irreducible in T. So it's very natural to ask, when is T a half factorial domain? Well, T is an HFD if and only a boundary 1. So if the boundary 1 for all of our irreducible alphas, then it's an HFD. Okay, so we'll assume that T is not equal to K because the result is kind of easy then. So first we'll assume that T is an HFD. And, alpha is in irreducible of T with boundary alpha n bigger than one. So what does this mean? This means that I can write alpha this way for some choices of I or negative J irreducibles in R. Of course, this may not be the only way to write it, but there is such a way to do this, right? And here we're going to get a very quick contradiction because we have alpha I1 A plus N. What do you suppose is the key observation at this point? I'm sorry. Right, but how do I know that these are irreducible factorizations?
Irreducibles and R remain irreducible.
That's the important chunk of it. Alpha, J are all in the irreducibles of T. Alpha by assumption, and because pi are irreducibles in R, they remain irreducibles in T power 3 is gone. Therefore, K plus 1 is less than. And this is a contradiction. How about the other direction? That is, suppose that we have the boundary of alpha is always equal to 1 for any irreducible. Well, that one is pretty good. So now suppose it's boundary of every irreducible, our boundary is 0. Let right, alpha 1 to alpha n, beta 1, beta m. Alpha I, beta j, n, irreducibles to T. So applying sum and since each of these are 1, I get n. There we go. Now, there's one, I've kind of hoodwinked you a little bit. My glasses don't work so good, but I think I skipped over something. There's one important thing that I need to do here. I need to show it's atomic, don't I? But how do we know? So, sort of after the fact, and this kind of illustrates the importance of this no non-unit being a boundary 0. Should have noted P must be atomic. Because really all I've shown here so far is that everything can be factored into irreducibles, does so with equal lengths. Right? But why is it the T is atomic? Oh, that's too fancy. In fact, this might be easier. T is CCP under these conditions. Right. Here's the reason why. Suppose we have an increasing chain of prime ideal, or not prime ideals, principal ideals. If any AI is a unit, then this terminates. Well, at least it stabilizes. And I'm also going to assume they're not zero because I'm not stupid. So, was mostly. So if you look, for this strictly, if you have this containment, AI, strictly contained in AI plus one, this means that AI plus one times R is AI, correct? Now take the boundary both sides. Well, let me say with R not a unit. Right? If it's strict, R can't be a unit, right? So take the boundary of this. Boundary R. Boundary equals boundary R. But this is greater than 0. Right? If it's not a unit, which means so let's say because you've got a countdown on the boundary, right? And because T has no non-units, a boundary 0, then you have to stabilize. Otherwise, if you didn't have this, then what could theoretically happen is you'll hit some point where you have a non-unit of boundary 0 and you can just keep dividing, right? But here, having no non-units of boundary 0 puts a stopper on this. It gives you ACCP, and hence it gives you autonomy. Okay, any questions on that? Let me give you a quick definition and final theorem for next time. Definition. Let R be an order and bring up integer. So what do I mean by this? I mean, R bar is the interval closure R and R and R bar. Which I guess is implied by the previous statement. So think, for example, I. This. This is the set of X in R bar such that, X R bar is contained in R is the conductor ID. It is the largest, it is the largest shared ideal. I mean, as a set, it's the same set. I think that's fairly easy to prove. This is called the conductor ideal for this order R. So I'll give you a theorem here. If R is an order in ring of algebraic integers R, R will say, and I is the conductor, part of our body's largest shared ideal. This is always non-zero for rings of algebraic integers. If X is not in any prime ideal containing I, because remember, I is an ideal of R bar, so I can factor it into prime ideals. And if X is not in any of those, then there is a power of X that is down in R. Then X to the n is in R. This is actually kind of useful, and we will use it next time as we explore what happens with HFDs and rings and integers, and also in polynomials. Any questions? All right. Well, I will see you folks then on